Hello, physical science students, and welcome to our section on thermal energy. We are going to talk in this video about temperature and heat. And some of the topics we'll be covering, we'll look at temperature. We're going to ask what's thermal energy, what is heat, what's specific heat. We're going to find out how to calculate change in thermal energy, and we're also going to look at how we measure specific heat. So let's start with temperature, because we all use this word a lot. We take the temperature of the surroundings. What is the temperature outside today? Well, what are we really talking about when we talk about temperature? If you have a fever and we take your temperature, what does that mean? Well, temperature is the measure of the average kinetic energy of all of the molecules, of all of those particles. How fast are they moving? Temperature tells us their average kinetic energy. Therefore, if we have something that is cold, a cold liquid, and we're measuring it, there will be little movement. The colder something is, there will be less kinetic energy of those molecules. Remember, kinetic energy is the energy of motion. If we have something that is hot in temperature, it has a high temperature, the average kinetic energy will be high. So those molecules, those particles are going to be moving around at a greater velocity. So let's look at some units of temperature. In our culture, we are mostly familiar with the unit of degrees Fahrenheit. Unfortunately, degrees Fahrenheit is actually, the degrees are different in magnitude than the degrees for Celsius and Kelvin. The SI unit is actually the Kelvin. It's symbolized with a capital K. It's based on the idea of absolute zero. If you want some advanced proficiency, look into what that means. What am I talking about? And what is the Kelvin scale and how does that work? That is the official SI unit. Most of the time in science we'll use degrees Celsius. A lot of the times we will, even though it's not the official SI unit. The actual size of the degree for Kelvin and Celsius are the same size. Fahrenheit, however, is a completely different size of degree. So let's talk a little bit more about energy and temperature. Remember, the average kinetic energy tells us the temperature. That's what temperature is, the average kinetic energy of all of the particles. And when they increase in speed, the particles, they increase in kinetic energy. And here's an example. If we look at those little arrows as being proportionate to their velocity, these have little velocity and these have greater velocity. This would be a lower temperature than this because this is a greater average kinetic energy of the molecules. What about potential energy? Well, if the particles have a greater separation in space, if they're farther away from each other, there will be an increase in their potential energy. So if they're closer together, we have less potential energy, and when those particles are farther apart, we have greater potential energy. Now let's look at thermal energy. We've been talking about kinetic energy and potential energy. What about thermal energy? What is thermal energy? Hopefully you get some idea, when you think of thermos or thermal underwear, we're going to keep warm, right? Thermal has this idea of warmth to it, heat, something like that. In science, when we talk about thermal energy, we are talking about the sum of all of the kinetic energy and potential energy of those particles. So once again, it's similar to the idea of mechanical energy. Remember, mechanical energy in our last section is the sum of all of the kinetic energy and the gravitational potential energy in that system. Well, thermal energy, surprisingly, is very similar. It's the sum of all of the kinetic energy and potential energy of all those little particles. If we increase the temperature, what happens to the thermal energy? Well, we know that temperature is the average kinetic energy of all those molecules, how fast they're all going about, and the average of that. So if we increase the temperature, we're increasing the kinetic energy, right? We're putting more kinetic energy into our system. And therefore, if we're increasing the kinetic energy, we're going to increase the thermal energy. What if we increase mass of the particles? What is that going to do to our thermal energy? Let me ask it in an illustration. Let's say I have a tiny little cup with water in it, and I have a large glass with water in it. Which one, if they have the same temperature, so the average kinetic energy of all the molecules is going to be the same in both of these glasses. One has a tiny bit of water and one has it's a large glass of water. Which one will have more thermal energy? Well, thermal energy does depend on the mass. There will be more thermal energy in the larger glass than in the smaller glass. So to summarize here, when we are talking about thermal energy, it is the sum of the kinetic energy and the potential energy of all the particles. If we increase the kinetic energy, we increase the average kinetic energy of all the molecules, or increase its temperature, we will increase the thermal energy. If we increase the mass and the number of particles that we have, we will increase the thermal energy. Now let's look at the next question. What is heat? You all know the answers to these questions, but I'd like you to try and work on practicing explaining them using scientific language. Heat is the energy transferred between objects due to a temperature difference. So if we have a temperature difference, heat is the energy that's transferred between those objects. For example, there is a pot of boiling water, and then there's the air around it. Warm objects always heat cooler objects, never the reverse. So in our example here, with the boiling water, we have heat being transferred from the very hot liquid water to a cooler air environment. So we have energy being transferred, and that is what we're talking about when we talk about heat, the energy transfer between objects due to that temperature difference. Another way to think about this, if it helps, is just that the heat content of something is the total internal energy. So here's a question for you. Can two containers of the same liquid, the same liquid, with the same temperature have different heat content? Well, the answer is yes. That heat content is that total internal energy, or that thermal energy, the heat content. And certainly, remember, the thermal energy depends on mass. And if I have a much greater mass here, this will have a higher thermal energy, a higher heat content. So I know this is a lot of vocabulary, a lot of ideas floating around out there. You might really need to review some of these ideas and some of the vocabulary to get it straight. We're going to talk about something next called specific heat. And it specifically is a different idea than just heat. When you observe different materials, I'm sure you know this, different materials heat up at different rates. Not all cooking pots are the same. I don't know if you've ever camped and used different metals or different kinds of pots over a stove, but they certainly heat up at different rates. Here is an example, a kilogram of gold and a kilogram of aluminum. If we try to heat those up, gold heats up about 7 times faster than aluminum. That's because different objects possess, different elements, different materials possess different amounts of specific heat. Specific heat is the amount of energy needed to raise the temperature of something. Specifically, by 1 kilogram 1 degree Celsius. So it's a very specific unit. We want to raise 1 kilogram of the substance by 1 degree Celsius, and the amount of energy needed to do that is that object's or that substance's specific heat. Here are some specific heats of different common materials. So remember, specific heat has to do with how fast you can heat something up, or conversely, how fast it can cool off as well. If it heats up quickly, it'll cool off quickly. If it takes a lot of energy to heat something up, it will also cool off much more slowly as well. One thing you must know, water, the amazing substance on Earth. Water has an incredibly high specific heat. The high specific heat of water is what allows all of us to live on this planet, or any life to live on this planet for that matter. Water can absorb a lot of thermal energy and change very little in temperature. Think about the implications of that for life on Earth, not just for organisms, but environments as well. And think about how this impacts coastal environments versus inland environments. That's why inland environments are very harsh with dramatic fluctuations in temperature, whereas an environment that is next to a very large body of water will change very little, because water has a very high specific heat, and it is able to change very little in its temperature. Really humid places will fluctuate a lot less in their temperature because of that high specific heat of water. So let's look at a formula, an equation, that helps us relate some of these different ideas mathematically to each other. And you will not have to memorize this particular equation. It is a very useful equation, and you will need to memorize what the different variables mean and what they represent and how to use the equation, but I won't make you memorize the equation itself for a test. So please know how to use it, however. The relationship between all of these things we've been talking about. Q represents change in thermal energy. And anytime we have a change in energy, it's going to be in joules. So Q is in units of joules. M, little m, is always mass in kilograms. These capital T's, capital T always represents temperature, as opposed to lowercase t for time. So we have temperature final, little f means final. So final temperature minus initial temperature. And that temperature is measured in degrees Celsius, the change in degrees Celsius. And capital C represents specific heat, and it's measured in these units here, joules per kilogram degrees Celsius. So to use this formula or this equation, we're going to practice a little problem and walk through it together, and then hopefully you'll be able to do some of these on your own. Let's say we have a wooden block that has a mass of 20.0 kilograms, and we are told what its specific heat is. Remember, the specific heat is how fast can it heat up and how fast can it cool down. Find the change in thermal energy of the block as it warms from 15 to 25 degrees C. So let's go ahead and write our formula down, and we're going to plug our values in of the things that we know, the different variables that we know to solve this problem. Here's our equation. We know our mass is 20 kilograms. So 20.0 kilograms for our mass. We want to find the change in thermal energy, and that would be Q, so change in thermal energy in joules. And we don't know that, so that will be our variable. We would like to know these things here, TF minus TI. Remember, final temperature minus initial temperature. So the block is warming from 15 degrees to 25 degrees. So the final temperature there is 25 degrees. And the initial temperature is 15.0 degrees. So that's final temperature minus initial temperature. And the last thing we need to find out is the value for C, the specific heat of this block of wood. And we're told that it has a specific heat of 1700 joules per kilogram degrees C. That joules should be capitalized. Sorry about the typo there. I can go ahead and begin to solve for this problem. I can say 25 degrees minus 15 degrees is 10 degrees C. And I kept all my other variables the same here. And I did this specifically so that I could show you where units are canceling. I know my degrees C here is going to cancel with these degrees C. The kilograms are also going to cancel. The units at the end of this should just be joules. So when I plug this into my calculator, 20 times 10 times 1700 gives me 340,000 joules of energy. That is the change in thermal energy of the block as it warms from 15 degrees to 20 degrees. Last, we're going to look at how do we measure specific heat? How do we come up with numbers for this? And calorimeter is a device that is used in science to determine specific heat. And I'm going to explain how it works. It's really neat. First, I want to rewrite our little formula for the thermal energy equation. I want to have this thermal energy equation on hand for us so that we can understand what it is we need to measure in our calorimeter and why we're doing what we're doing. Let's say we have some unknown substance, this orange substance of matter, and we'd like to determine what its specific heat is. We can do that using this calorimeter if we heat our sample up and then we place that sample inside of our calorimeter inside this water. When we set the calorimeter up, we know our mass of water, we determine, we make sure we find that out before we start the experiment. We know our mass, we know the initial temperature, and we record that. After we put our sample in, heat will be transferred from that sample into this water, and we will take a final reading on the temperature of the water and determine then what the change in thermal energy was in our system here, because we know already what the specific heat for water is. We know the mass of water, we know the change in temperature of water, we know the specific heat for water. So for our little experiment, we can determine the change in thermal energy for it. From there, we can calculate the specific heat for our unknown substance or known substance, whatever this is, because we know the change in temperature. Hopefully we have measured that and recorded it well in our lab notebooks. We know the change in temperature of it. We should have taken the mass of it initially, so we know the mass of it. And we know the change in thermal energy, because the amount of the thermal energy that was transferred from the substance to the water we know it. We just calculated it for water, didn't we? That change in thermal energy. So since these will all be known values, we can then determine our specific heat for that substance. Quick review. You need to know the definition of temperature and what is temperature. You need to know what thermal energy is, what heat is, what specific heat is. Both an explanation and a definition. You need to know how to calculate a change in thermal energy. So you need to know that thermal energy equation, how to use it. You do not have to have it memorized, but you need to know how to use it, and you need to have the different variables memorized as to what they mean. You need to know what it is we use, what kind of instrument we use to measure specific heat, and have a kind of an idea, be able to explain that, how we would go about using that calorimeter in order to measure specific heat. Here's some advanced ideas. Certainly, there are many more advanced ideas. If you're really interested, we could see if we could let you set up an experiment. I do have a calorimeter down in one of the labs. So if you're interested in doing anything like that, please talk to me. I'm excited to see what you have to come up with, what kinds of things you're interested in, and we'll see you in class.